Okay, so hopefully by now your slides have been pulled over. By the way, this week, just a quick announcement, we still have our 2-week lab going. And so we don't, there's no formal meeting with the lab. You don't have to meet. Um, I will be, I mean, obviously I'm available on Slack, but I will not be logging in. And so please use this time wisely. I guess you can use this time in 3 different ways. One, you could go over your notes and kind of look at the data and kind of like wrangle the data. That's the first way you could go. Or you could spend the time to actually work on the lab itself, to actually kind of do your work on that lab and get it ready. And by that, I'm talking about actually like running your correlations over the psychology data, and also maybe running some t-tests and some linear models. One thing I will say though, before I get to the third piece, is that when you're looking at your data in psychology, one thing I've noticed about data from psychology is that you tend to have um, a lot of data. It's a lot of data. There's a lot of different columns of data to look at. And so it's for that reason that the first thing that I've asked you to do in the lab, the very first thing, is to run your correlation studies. Now, your correlation studies are not the causality, or it's not like actually telling you what's going on between your sets of data, but rather what it's doing is you're looking to see. Let's get back here. What you're doing is you're looking to see how, for instance, one variable may be somehow related to another. And that's really where you want to start when you're creating a model. In fact, you want to kind of study that variation and say, how does this variable over here impact this other variable over there? And so that's why you'd run a correlation test. Now, in the actual lab itself, there's this code for a function called the pairs panel. And the pairs panel will produce a giant kind of a grid of, on the, I guess on the left-hand side, you have graphics of the plots of the x and y coordinates of each of the points. And the other side, you have your correlation values. Now, what I would recommend is that because there is so much data, psychology data sets, you look at the correlations between certain variables and say, aha, between, I see this a variable for question 1, another variable they use for question 4, for instance. And you can say that since the correlation between question 1 and question 4 is so high, perhaps there is some kind of relationship that exists between these things. Actually, in psychology data, there probably is a relationship, and that is that the question 1 and the question 4 are probably asking the same question. The question in a personality test, question 1 might be, I feel comfortable when I talk to my peers, and then question 4 might be a question asking, I feel as if I'm able to voice my concerns when I'm speaking to my friends. So it's different words, but they're actually asking a very similar piece of a very similar piece of your personality. They're going after a similar piece of your personality in that question. And while the participant who takes that test will not know what that those two questions are actually asking the same thing, the analysis of the data will show that perhaps they are. And so in your result here, what you're doing is you're looking at your correlations, and that's you find that question, or the variables for question 1 and the variables for question 4 are very, very closely related. You might run a t-test and find out that they're actually target both ways, I can think. You might run a t-test and say that question 1 and question 4 have absolutely nothing going on with each other. That means there's no difference in those two different two columns of data. Whereas if you chose question 1 and another question, which is completely different, you might find that there is a difference. And so you could use your t-test in that case to argue that question 1 and question 4, which are essentially the same question, have little difference between them because they're asking the same question. However, question 3, which is a completely different angle of personality, if you ran a t-test over there, you might find that, and a correlation too, you might find the correlation is different and that the t-test is different. And you might say that just going by my data, I see that that they are actually different pieces of information. And so then you can go back to the questions and say, I found it. I see that question 1 is about the feeling comfortable with my peers, and question 3 is I like being by myself. It's, something it's like a slightly different question, but it's still I mean, it's asking a different kind of answer, but it's still a personality question. But you can see that the questions are actually scoping a different piece of one's personality. Anyhow, these are just some ideas that you can try, and just to kind of get an idea about how you can analyze this data. Remember, there are no right or wrong answers. All I'm expecting you to do in this lab is to explain that your approach is actually uncovering some kind of relationship. There's some relationship there which is relevant to the study. Now, the third thing that you could do, if we're not meeting on Friday for our lab, is just to get some rest, because it has been a tumultuous week, I can tell you, and it's been just absolutely insane. And I think that we're looking at some pretty cold weather in front of us for a couple of weeks here. And so maybe use this time to get some air. I know it's kind of ironic for me in, in this class to tell my students to stop doing their homework and getting out, but I think though that in the grand scope of things, you'll find the time to get your work done, and many of you have been doing that. But I think that perhaps maybe there should be some time where you can have some look after yourselves and maybe just get some downtime in some case here, and to just breathe, because I think that when I think about the weeks of winter which are in front of us, or the months of winter which are in front of us, I think of nice weather like this that we have outside. I'm thinking, why not get some sun, because that will do you much, much better for your health than it would be if you perhaps buried yourself in your books. You can always do your work when it's dark, but I would say that maybe get some rest. So it's up to you. First thing you can do is to wrangle your data. Second thing you can do is actually run your code on the data. And the third thing is just to get some air. So it's up to you. You have plenty of time. And just as long as your lab is done when it's supposed to be, then that's fine. Are there any questions? Let me just ask anyone out there. If you have any questions, please unmute and just go ahead and ask, and I'll be glad to handle any questions you have over your lab quickly. Or if you don't have them now, then you can always use Slack later on. And I do have office hours. Anyway, I'll leave that here. And if you have questions, let me know. Let's go back to the slides here. The slides, I'm not exactly sure where we left off. One thing that I might mention, though, is if you can't remember where we left off in class, or whether if you miss class or something happens, I mean, life happens. It does. If it does, then, for instance, I invite you to go to the course website, which is right, let's see, where are we now? Data analytics. And you can go to, for instance, planning your time, which is down here, and you can see what to expect. Now, what to expect, we have week 12, which is like around the 20th. That's the 20th of November. I'm thinking that we'll have our exam too. So that should be on your radar by now. We also have, let's see, next week, where we have Dr. An-Yi Wu, who's going to come in and talk about his research with data in economics. He is a wonderful, wonderful speaker, and you're guaranteed to get goosebumps whenever he says anything. So anyway, please do come to that. So there's that. If you miss class, you can always kind of get an idea about what we're talking about. I still need to update some of these things. We're not exactly on machine learning yet, but we will get there. Another thing I want you to think about is use the YouTube channel. So it's right down here. If you click on class videos, this link there, hopefully you'll see this coming up. These are the classes that we have had, and so I record the lectures and the discussions that we have, and I put them up here. And so, for instance, you can click on the playlists, and you can go to full playlist for analytics. You can see that we have all these classes here. And just recently, I put up speaker Lydia Eckstein's psychology discussion. And so if you missed that, please do watch this video, because it's actually quite exciting. I think that she's a terrific speaker. Okay, so I'm going to go back now to these slides here. Hopefully you would have pulled them from your repository by now. Let's see, where did we end up? We're talking about different kinds of models today. Now, the models are actually very important for our lab. And so please do spend some time looking at this code here. But actually, the t-test code, remember, comes from our class from last week, the previous slides to this. And so you have that code there that you can reflect upon. Now, we're using models to ask some very basic questions, which actually to actually find the answers, you have to explore what's called historical data. And historical data is really saying, it's really meaning that you're looking for patterns that have existed in the throughout the I don't know throughout along like as long a time as you can. You're finding patterns and you're using those patterns to make a prediction. Look at the question that we have here. Do taller people make more money? Now, that suggests that we can go back in time and look at all the salaries from all the people that we could find, and then to compare that with how tall they are. So that would give us a historical view of whether people who are tall tend to earn more money. Now, the other side of this question, though, is, which I haven't written here, but it's saying things like, can I make the assessment, or that can I generalize that tall people tend to make more money? And to do that, to make a generalization, you're really talking to the predictive nature of the model. You're saying that if I were to see new people coming into my data now, and if I were to see that they are tall, could I infer that they're making more? Not tall. You'll find actually, I'll cut to the chase here, that taller people do it, in fact, tend in general to earn more money than people who are not tall. So that's a question that we're asking, and it has a predictive nature to it. This other question that we're asking here, question 2, do hotter places tend to have more crime? In other words, do places with higher annual temperatures tend to have more crime? And again, to answer this question, you can't, I mean, of course, it's a yes and no question, but in order to answer that question with any authority, you will have to go back and look at historical data. In other words, you have to look at a place, you have to look at how much crime they had, and then you have to look at their temperatures. And then one part of the question that is not necessarily written here is that we're asking for a prediction that if you show me some temperatures of some place, some yearly temperatures, can I infer in general that there may be more crime there? Now, I use the word there may be more crime, or there may be, in general, there may be the likeliness that taller people make more money. You can't say definitively that it always happens. In fact, it's dangerous to do so, to say that yes, tall people earn more money. Yes, hotter places have more crime. You shouldn't say yes, they always do, because then you'll find somebody else with an opposing data set and will say, actually, I ran the same test and I found nothing. You must be wrong. And so don't set yourself up for that kind of argument, because you can't win that argument. You're using your data set, they're using their data set, and then it just goes back and forth and you never reach anything. And in fact, if anything, it just makes people who would have been friends into adversaries. And so what I would recommend is to say, according to the data set that I worked with, I found that taller people make more money. And that is why in your lab, I'm asking you to cite your data source, because the findings that you find there are not spread across the board in all psychology, but rather those findings are spread only to that data set. And so the data set that we work with for here, these findings are found with this data set. But we're extrapolating this and saying, in general, if this data is general enough, then we could say that taller people tend to earn more money. Or if the data set that we have here about the temperature of a place and the crime that it has, we can say that this place shows that trend. And so I'm going to argue that if I use this data, then I can say that yes, it tends to happen, but I wouldn't be surprised if someone shows me some other data where it doesn't necessarily happen. So what I'm saying is that everything is data-centric. All these resources are data-centric. But the bigger the set of data that we have, the more globally we can say something is happening. Anyway, that's just I'm just venting there. But so we're going to use something called modeling, actually, to ask these what I call what-if questions, where, for instance, we're going to take the data, pour it into some kind of into a technique, if I will, if I can say that, and we're going to then kind of look at the trends which happen in that data, and then say if those trends are still with us today, and I will argue that they are, because the data hasn't changed, or the trends or the human natures that are involved haven't changed. That if they're still with us today, then that we'll say that we can actually throw in some numbers and see whether, for instance, see what the model would suggest is going to happen. In other words, in general, when I have people who are tall, what kinds of money can I expect them to be earning? So those are the types of what-if questions. Another thing we discussed last time in class was that what our model really looks like is a nice straight line. We're taking all the data and converting it into a line, and then we're just checking to see where things fall on that line. And so this is what an ideal mathematical relationship would look like, where you have temperature and crime, and everything seems really kind of cut and dry, where there's no I would say here there's no reason for statistics because everything falls on the line. Everything is perfectly in alignment. However, in the real world, in fact, you have this function here where you can actually kind of follow that line. But in the real world, your data doesn't fall perfectly on a line. Instead, the data is kind of like all over the place, and it is up to the model to actually create that line. And so this is really what the model is doing. In this case here, it's looking at these points and it says, well, I recognize that these points are kind of scattered, but they do kind of collect in a certain linear path for the far left. The middle one kind of they collect in a kind of a curve, and then for the far right they kind of collect in a different kind of a curve, which is shape. But the points do collect in a way that I can say is a pattern. But in reality, though, most of your points are going to be all over the place like this. And so this is why we need these models, because it's very difficult to figure out exactly where that line is supposed to go in our data. If we were working with this, where we just had a function, then it's easy. But we don't have that. We usually get this. And so what we're doing is we are creating a line. We're actually creating this nice, easy function from this mess, which is our data. And so then on that line, when we have a line equation, we can start throwing in values of our own and see whether these values, we'll see how they behave and see how things are and see whether something is actually whether we can build a model to actually predict. So if someone comes in our office here or our door and they are of this particular height, could we take that height, throw it into our model, and then see those points, or then kind of get an idea from these points about what their earning power would be in general. Of course, it's never going to be exactly 100% on the nose because that's just not natural. That's just not how it happen. But we're using these lines to kind of get an idea to infer. So that's what I ask. Well, that's what I mean by the what if questions. We're actually asking a question like, what if someone is tall? What if somebody is not tall? What if somebody is average height? What can we expect? I use the word expect in the statistical form here. Like, what can we expect them to be making? It doesn't say what are they making, but it says that statistically, according to our model that we've created from here, what can we expect them to be actually creating or to be earning? And that is really what these models are all about. But I will say one thing that is actually very, very important is that anybody who's watched the weather, where the weather person said that it's going to be absolutely gorgeous and it's going to be perfect, you should get your picnic stuff, get ready for your picnic, get your picnic stuff in order, pack your bags, go out to the sun, find a nice place in the park and just sit there and enjoy your picnic with all your closest friends. Anyone who's heard that and then actually gone to the park to find that it's raining would know that models are not perfect. The model that told the weather person that it was going to be nice and sunny was wrong. And that's because the data can change as very, very quickly in weather. And so provided that you have the data is consistent, that that means the temperatures and the wind and everything else is consistent and it doesn't change, then the model should be fine. In other words, if I'm creating these lines here and the points don't dance around, then my model is fine. But when I find that my points start moving around or changing as the weather does, then the model, whatever I did yesterday, means nothing today because the data now has changed and I have to create a new model. And so that's why, for instance, you have rain on your parades every now and then, or rain in your picnics, when you were told that it was supposed to be beautiful and instead there was a thunderstorm. So models are not perfect. They don't last forever. The data has a shelf life, and you have to look out for all of these things when you're actually building this. But still, models are actually very good points of reference for figuring out, determining certain trends that don't appear to change. We are actually using linear regression. That's that LM command in R, which is going to be looking over some independent variables and dependent variables, and is going to see how these dependent variables are kind of being swayed or controlled by the independent variables. Now, the independent variables tend to be like time or other things that cannot be controlled, whereas the dependent variables are variables that clearly cannot exist by themselves. The time studying and the grade point average graph that we've seen earlier, the amount of time that you're spending might be considered your independent variables because it has something to do with the time. Whereas the dependent variable could be the grade point average that you get, because you could argue very easily that the amount of, or the quality of grades that you have is dependent on the time that you put into getting them. Anyhow, so you have this plot right here. So the time spent studying and the time spent actually, the grades that you earn could be considered the time, the hours spent studying could be considered your actually I should call this the I think I have these things wrong here. I would call this actually the time the independent and the grades the dependent. I'll have to change that. These are, I think I got these confused, but they're reversed. So I would say that the time is independent and the grades are dependent. I have to go back and change. Apologies. Anyhow, so the model that we're actually creating though is there's no magic in it. So what it's doing is once you put all these points up on a screen like this, you have all these different dots, data points. This is supposed to be this first one that I'm looking at on the left, lower left, right next to the intercept equals beta naught. That's an x and y point. The x is the time, and the y is going to be some kind of observed, value, and that's where the point will land. And then as you move up and see these other points here, they're all points for which x is equal to some value and y is equal to another value. And so the model here, the mathematics involved, is to find a way of drawing a line right through these clouds of points. Now, in this case, it's kind of confusing because we only have 1, 2, 3, 4, 5. We only have 6 points, which really isn't enough. However, the more points you have, the better your model gets. In fact, that's talk about that in a moment here. Confidence levels. The more points you get, the better your model is. The better your prediction is. You're able to say, well, in general, most of my points have gathered very, very closely to this line. Therefore, I'm going to say that this line is actually a good fit. But you're really just looking to see how you can make a line equation. And here's your line equation here. Y is equal to a plus bx, or y is equal to mx plus b. It doesn't, it seems like every book has a different way of calling the line, but if you remember that the a is your intercept, and your b is the slope, and the x is the actual value. Here we go. These are correct. Independent and dependent. Go back and fix the other one. Not let us stray. Okay, so then we have, for instance, we talked about this residual sum of squares, and now in order to actually form a line between in a cloud of points, it's actually quite important to find a way that you can kind of put that line in very, very snugly in those points. And so if those points are gathered close together at certain points, then the line is going to be kind of well, it's more predictive, I guess you can say. Say that the line that we create is actually closer to the points than, for instance, another graph that we have here where the line is actually kind of far away from the points. And what I mean by that is this. And so look at the upper plot here. We have kilometers versus something else. Maybe it's but you can see that the difference between the kilometers isn't very much. The scale is not very much. It goes from 0 to 2 to 4 to 6. And so the actual distance between, if you just look at the y-axis here, not the x, but the y-axis between every point. The first 2 points, the distance is probably 0 and like maybe 0.3 or something. It's not a very big difference. The first and second points on the left-hand side of our line there's not a big difference there between those 2 points. And so the line that cuts between the line or the point at 0, which is the second point, and the first point, which is probably at 0.3, is very, very close to those 2 points. And so we can say that if more data were to follow and it were to stick to our line here, we would expect them to be kind of close to those 2 points, 0.3 and 0. And so our line would actually be making a good prediction. However, look at the lower plot, where the difference between the first and second points on the left side of the plot could be much greater. I would say that perhaps it could be 0 and 500. The first point could be 500, and then the second point could be located at 0. And so the line has a lot of play. It could be placed anywhere between 0 and 500. And so if someone gives you data, or they're asking you for a prediction where they're saying, I have a point, I have a y value, or I want to find the y value at between those 2 points. There's a lot of play. There's a lot of, I mean, there's a great distance between those 2 points, and so it could be anywhere. It could be the next y between those 2 points could be anywhere between 0 and 500. Whereas in the upper value, or the upper plot, the y could be found anywhere between 0 and 0.1 or something. And so that's actually a smaller distance. You're kind of you're squashing that in between y value between 2 points in a smaller area. Anyway, what I'm actually talking about there is called the residual sum of squares, where your RSS, as they call them, RSS, if it's a big number, it means that there's much more play between the points, and maybe the less accurate your model could be. Whereas if it's a smaller number, if you're comparing 2 points here, usually means that your line is kind of more tightly packed between points. An idea that those points you have there are actually giving you a tighter, more accurate fit. You have a better idea about where points may fall. Whereas in the lower plot, it could be anywhere. I know I have points here, but I'm not exactly sure whether my value of y could be found between 0 and 500. It could be anywhere between those 2 points here, and it would be difficult to actually get any strength out of this model here if I have such play between my values. I think that if you spend some time just staring at this, after a while it will click. If what I'm saying right now doesn't make any sense. But just remember, though, that we're trying to find a better fit. We're trying to find data that actually more correctly, or more closely, I guess I should say, more closely fits the model. And so smaller RSS values tend to be favorable over large RSS values. Anyway, so that's really what this is. This is your residual. This is the amount of distance between the expected, which is the line that your model is proposing, and the actual place where the point showed up. So here we see in this thing here 3 and 2.9 and -2. These are measurements between the actual data and where we predicted that those points should be found. When I say should be found, that's the expected, and I mean it's just a statistical way of saying this is where we would expect them to be, but otherwise they could be anywhere. But we would expect them to be here, and the closer they are to that line, then we'd say the better the model is able to predict the points of our set here. Now, looking at these points here, just by the by, 3 and 2.9, I could argue that these points are actually outliers. I mean, they could be very well outliers, because I mean they are such big numbers. It seems like around 3, where y is equal to, where that first green 3 is equal to, and the next green 2.9. That's a great distance from the model itself. And so before you start thinking about throwing those points away, as you may do, you might think, oh, these are crazy points, which are really throwing off my model, and it's really, really bad. Before you proceed with actually throwing these points away, take some time to look at them to make sure that perhaps maybe they're not completely crazy points here. Maybe those are the points that that you should be looking at, because they are so different from everybody else. Maybe, for instance, there's something going on with those points that's going to take your research into an area. A good example of this would be, I remember when the iPod from Apple came out. That was kind of a fluke, actually, on Apple's. I mean, they discovered this in some ways by accident, where they ran a survey and they found out, they asked people, what kind of music do they like, and what kind of songs do they listen to, and what would they like to do with their songs. And they found out that many people wanted to carry all of their music in their pocket at one time, because people went to the gym, they went jogging, they were working, they went to the library. They were in many different situations where they required, and any music aficionado will tell you this, but they required different kinds of music to work. When you went to the gym, you had different music than when you're working with when you were studying. It's a different kind of approach. And so they found out that from these outliers, that people wanted to have as many of their songs as possible actually in their pocket, so that when they went to these different places, the gym, school, library, shopping, work, uh, home, dancing, all these things, when they went to these places, they had that music selection there. This was totally unheard of at the time. I mean, today it makes perfect sense because, of course, we all love music. We know that all music doesn't fit everywhere. But at the time, though, people would take a CD with them, and they'd have like they'd have a CD player, and they'd have like their gym CDs, and they'd have their work CDs, and then they'd have their library CDs, study CDs. But they were saying that they wanted to have all of the music, and that was a kind of a fluke that they would that they discovered. The researchers at Apple discovered when they were looking to see whether their market would be acceptable of an iPod type of player. They could have thrown it away, but they didn't. They said, "Oh, that's interesting. Let's explain why people want so much music on them." They went back and they found out that actually it's because people want they want to take their iPad or sorry their iPod. They want to be able to take their iPod to all these different places and not worry about him. Right. So anyway, this is just the line equation that you'll use. This is kind of like this math that we're looking at here, actually making the measurements of how far each of these points actually shows up from the actual model line. This is all stuff that we don't have to worry about. In fact, our studio and our programming language handles for us. We never actually see these things, but we do have this measurement of RSS, and so we can tell that bigger RSS values tend to be less accurate than smaller RSS. So if given a model, I would say in general, if you have two different models to choose from, maybe choose to work with the model that has the smaller RSS value first. And we look at them both, really study them both. But I would say that perhaps your model is a better model for smaller RSS values. But of course, that depends on the data. And so only I mean, you'll have to go through and see, and only you can see whether. Okay, so let's go back to our question here, where we're talking about crime. Is crime influenced by the yearly temperature? I don't know that we had time to do all this. I may as well just run through this quite quickly. I'm going to go ahead and just copy out this code. I'll just do this just because it's an interesting thing. Come with me, if you will, to my studio editor. Boom. Welcome back. I'm going to go ahead and just dump this all here. Oh, and of course, I need to things look pretty here. I call it data C crime setup. Okay, I'm going to do all this. I'm to organize this here. I'm not memorizing the code. Rather, I'm just looking back and forth at this and seeing that everything's. I think we may have done this. In fact, if I go here, I think that we may have already put together. Yeah, so we have the code already here. In fact, I'll go back to the notes that we have from the 29th. So remember this first thing over here. I'm going to run this just to get rid of any old stuff any old variables that are sitting around. Of course, right now I don't have any variables, but if I did, then I'd want to get rid of those. I'm going to load my file.choose. And of course, you cannot see what I'm doing now, but what I'm doing is I'm actually going for my crime.csv file, which you'll find in your sandbox. So this just gives you a way of locating that file. It doesn't actually load the data. In fact, if you look at C, let me just show you something. C is just it's just where the file is located. It's not the data. And the reason why I'm saying this is because some of you have sent me emails over the weekend, over the break here, this last 2 days, saying that you've been trying to run this same code, and at this point here, everything seems to break down where you can't run the same thing. Remember, this just gives you a string, which is a file name. That's it, and the path. We have to still load the data, and that's why I have this. If I run the crime here, you can see that in your global environment, the crime actually does pop up. Now, you have abbreviations for different states. You have the lows. This data set works by low data sets, like low temperature. Not necessarily hot temperatures, but they're going by low temperature. That's their take. Then we have, it's always kind of scary when you see a data set that just says murder. That's some kind of measurement. I'm not exactly sure how that measurement was taken. We'd have to go back to the code book and find out exactly how they reached 7.1 for Alabama. That seems a little scary. If that's a value. I don't know what that must be some per year type of crime wave. But we have this TC 2009, and this again we'll have to go back to our code book to see exactly how this comes together. but the curators of this data set used this variable here, 4,337.5, actually as a collection of other variables, I would think, which have been multiplied together or divided out, and so it's a measurement of crime. That's how they're using this. Anyway, but for this experiment though, we're going to assume that TC 2009 and low, these are the variables that we're going to use, the temperature and the crime, or the amount of crime that we see. So we have this code here. We've just run everything. We've just loaded our crime. That's terrible to say. We've just loaded our crime. I shouldn't say that. You do have this information in here. You can always go to the view, or you can just click on it. This is one thing that we can do. We can actually convert this into a data frame so that we can work with it as a data frame. In fact, I think I already have all this information. Yeah, here. So run this thing here. Now, this is going to help us with some of our code that we're working with. Now, the next thing we're going to do is we're going to just do some preliminary plots. Thumbs up. And this is, I would say, the first step. The first step that you want to do is to run a preliminary plot of your data. Anything that you're interested in studying, plot it out first. Actually get a visual and see what you think. Because if you look at the plot, sometimes you'll think to yourself, oh, there's something going on there. Or you might look at the plot and find out that nothing is happening. But this goes back to my RSS here, my residual sum of the squares. You see this shadow that we see? I'm looking at the plot right now on the lower right-hand side. But you can see how where the points tend to be scattered out all over the place. You find this, or we have, I guess in this case here, where the points tend to be like kind of not scattered out all over, but like they're closer to the line. It seems like the line is perhaps straighter, but the line takes a curve when that particular trend ends and the points become more spread out. But also, though, in this case, we have the shadow, which is your 95% confidence level, which is saying that the points, where I have enough points where I am to suggest that that this line is actually a good fit for this data. Now, I'm looking at the x is equal to 0, and the y is equal to just above 4,000, and another one that's just below 4,000. In other words, I'm looking at the last 2 points on the right-hand side of this plot. Now, we have this kind of funnel-shaped shadow that's there. And that's saying that I have so few points that I have no idea. I can't make any real accurate predictions about where those points are going to land. And so I'm not very confident the points are going to be in a very tight located, or a very tight location. They could be anywhere in that shadow. In other words, if more data were to come to me that follow this same trend, then I would say that they could go anywhere in this shadow. In other words, around x equals 0, according to the trends that I see here, there's really no accurate prediction that I can make about where those points would land. However, around x equals minus 40, because the data set's been kind of, or the points have been found to be kind of collecting in the same types of regions, that shadow we say there is saying that I would expect to find more of these points showing up in that region somewhere. So in other words, I have enough data to suggest that my points would actually land in that particular expected region. Of course, they could land anywhere, but this is just a kind of a notion that you have enough points to actually to make some assessment about where those points could possibly land, where they could be plotted in relation to your line. Or you could think of it in terms of like, how accurate is this line? Now, another thing I'm going to talk about here is that we'll go ahead and use a linear model. This over here, by the way, when we plotted this thing here, where this line, geom smooth, is just saying to find a line which helps us to kind of read the data. In other words, we're using the line to kind of get an idea about the general trend of the data set. It's not a linear model, but the next one is. So when I run this piece of code here, this is a linear model. And what I've done is I've created a smooth line, but actually the smooth line is in function of a model of the points. And you have to just say method equals LM, or linear model. And so this is really what your model is going to look like. And so if I wanted just to go ahead and make predictions and say, supposing x is equal to minus 10, where would I expect those points to show? Those points would show on the line, on that blue line right there. And so that is your expected But it's not necessarily where the points are always going to land, but it's where the points are expected to be. In reality, you can see that the points kind of show up all over the place. I would say that because there's so much play between these points, look at the first 2 points we have here on the left-hand side. One is at about maybe 3,500, and then the next point could be, oh, I don't know, maybe 2,700 perhaps, like around there. That's a lot of play actually between points on the y-axis. And so I would say the model is not necessarily super accurate. It would probably have a very big RSS value, which suggests that perhaps it's not, the points aren't very well packed together. So now we're actually going to create our model. We'll do that with this code right here. In fact, all the math that we've just been talking about is actually just this one line of code right here. A linear model for which we're regressing this TC 2009 over the low. So we're going to say that the low is your dependent variable, and this is going to be your your low is your independent variable, and this is going to be your. In other words, the way this thing is kind of formatted, if you will, if I can just kind of, oops, this is going to be like your y is equal to mx plus b, and so your y is going to be your dependent variable. So this is your dependent variable. So give it one. And your x is going to be your independent variable, and that's where this is going to be here. And so if you think of it in terms of this, then perhaps this will help you to kind of remember how you can remember where these points are. Who's who, dependent or independent. Anyway, there's that. Now I've just created my model, and I'm going to now get a summary of that model. That means when I click on the summary, I have all this information that comes out of it. Now, one thing we discussed last week, the first thing I look at that we discussed last week is the p-value. Remember, we spent some time actually looking at p-values. How do I know that this model is any good? It doesn't matter. I would say, to me, in my mind, it doesn't matter anything about what these points are here. It doesn't matter any of those points if the p-value is no good. That's saying that if the model is not actually doing a good job of driving the influence of my predictors over my dependent variables, then it's not a good model. And so remember the test that we have. You're looking at your p-value, and you're seeing whether your p-value is between 0 and 0.05. If that's the case, or 0.01, this is a very small p-value. In other words, the smaller the p-value, the better the model is. But it only counts when it's less than 0.05, because it's like small but not that small. Then it's no good. You have to throw it out. So we have some other things we can look at. We have, like, for instance, our intercepts, which are actually rather important. That intercept over here, that value is this value here, b. And then we have our low. That value here is going to be our x value. And so when we were actually creating our linear equation, let's go back and do this again. I know that we've all seen this before. Our actual value to create this linear equation going from here would be this, where I have 21.65 as my slope. And then for b, I'm going to take this value here, 56.86. I'm going to throw that right here. And so this is actually the line equation that we see on this graph here. This blue line, actually, if you were to go back to algebra and to plot this out, or use your graphing calculator, or whatever it may be, you would find this blue line, and that's how the blue line is actually reached from these coefficients right here. Of course, you have some other things here that we'll talk about later on. I don't want to go too quickly here, but we have all these different types of pieces of information that we're going to go through. Another thing I look at is this r squared and adjusted r squared. In fact, we'll spend some more time actually talking about these things, I think, in our next slide set. But the adjusted r squared is kind of like you're looking at all the points where they've been kind of weighed so that they can actually be compared. Whereas the multiple r squared is kind of a per model basis, I guess, if you want. But I think that if you have models, you have different models with different models with the same data set, then I would tend to look at the adjusted r squared, because that allows you to compare your variables across models. Whereas if you have multiple r squared, that really means that this could be a more model specific value. But really what the r squared is saying The name doesn't help you understand anything about what it does. But it's saying how well do my independent variables describe the movements of my dependent variables. So, for instance, going back to that plot where we're talking about the more time you spend studying and the better your grades, or is an indicator of your grades, you would expect to have a very high r squared value, and that means basically a number that's close to one. It varies between -1 and 1, but the bigger the number is, the closer you are to 1, the better your independent variables are at showing how the dependent, or I'm getting all confused here. The better your independent variables are at predicting what's going to happen to the better your predicting variables are at showing the movements of your independent variables. So that means that if you have like a high value of r squared, it means that your model we're suggesting, back in the case of the study time and the grades, a higher r value says that it's true that the more time you spend studying, the better your grades are in general. It's a better predictor. The time does predict the grades. And here, in this case here, this is 0.2. It's not super great. It means that 0.2, it's saying that in general, I guess you can say that the temperature does predict this other variable TC 2009, but it doesn't say everything. In fact, there is still, this is only 20% of the story. There is still 80% out there. That means 80% of something is describing the variability in TC 2009. Yes, sir. Question. So the question is, I guess, what is that? What's in that 80%? That would be error. Yeah. So the question is then, so this value. I mean, this is, well, I don't want to say that talk about the error term just yet, but what we're saying is that the question is that, well, if we have 0.24 for our adjusted r squared, what is it what does it take to get this thing up to 100% so that we can say that our dependent variable is perfectly or sorry, our independent variable is perfectly explaining our dependent variable. What this is saying is actually that this is just one independent variable, which is the temperature, which is low. Just one variable. But actually, if we were to get a better model, this low r squared value is suggesting to us that we need to go back and find more variables that we can run. Actually, more variables to throw into this model. In other words, temperature and something, and it's probably several other variables. Other things are involved to actually explain this crime rating. It's not just the temperature, in other words. And you'll always find this, actually. You'll always find that it's not just the temperature. In fact, getting back to the model where we're talking about the more time you spend studying and the better your grades get, that's not always true, actually. It's not just the amount of time you spend studying, but perhaps it's the amount of time you spend exercising, eating well, how much rest you get, perhaps the amount of time you spend with your friends, the amount of the amount of sun you get outside, the amount of air that or clean air that you breathe. All of these things do make a difference. You could say that you spend all day, every day, every single for 12 hours studying, and your grades are still not very good. It doesn't always mean that the amount of time that you spend studying is going to be giving you better grades. How you spend studying, the environment in which you study, the living conditions, your overall mental health, your physical health, all of these things all contribute something. And so you don't typically expect to get a perfect adjusted R square score of 1 to say that this dependent variable is explained by the independent variables perfectly. It never happens. I mean, it never happens. I mean, it's up there, but it's never perfect because there are always other variables. In this case, the question is, how do we make sense of this 0.24, actually 25%, if you will. We're saying that actually there's 3/4 of something else, which are explaining, which we don't see, but which are used to explain this PC 2009. But we don't know what those variables are, and in fact, it's kind of frustrating to go back to our data here, and we don't have those variables actually in our set, which is a kind of a bummer here, because what it really means is that our analysis kind of ends here. So this is why, for instance, I was talking about that's a very good question. But this is why I'm talking about your psychology data, that you have many, many variables. You may find, for instance, that when you're trying to assess something as complicated as someone's personality, or what somebody thinks about something, or um, what they eat, or what music they enjoy listening to, there are so many different variables involved to kind of explore how someone chooses music, that you might find, for instance, that you'll never get the R² values that you want, but you get values that are good enough, and you'll say, but I'm going to argue these variables are themselves, just in this pool, good enough. But you'll always be looking to find other variables which would help to explain why somebody chose the music that they did, why they voted the way they did, or why they ordered food that they ordered. There's always that. And so don't become disheartened by the whole thing here. Just keep going, because you might find that some of your variables work better than others. And the story that you tell after your analysis can only be told using the variables that you have. And you'll say, and that's why I'm saying that according to you'd say that when you're describing or communicating your results, you would say, according to this data set, these are my predictors, and these are my dependent variables. Saying that using this data set, this is how my analysis is going to proceed. And so when you do that, you're kind of defining the game, if you will, or the rules of the game that you're using for your analysis. And so in this case, we're saying that the value isn't super great here, but maybe it's good enough for this analysis, just in absence of other data. But you'll never find that you have all the data. It just never happens. I know that was roundabout, but hopefully that answers something of the question. But still, it's a good thing to think about, though. How do I know that I have enough variables in my model? We actually talk about multiple variables in the next slides to come. And so there's more on this R² value to come. So we will come back to this topic. But in the future, though, as you're working on your models, though, just ask yourself, do I have enough variables in my model to help me get an accurate assessment of what's going on? This p-value, though, will help you to see that you do have the variables that you've chosen for this particular model are good enough. You can learn something from it. If the p-value were no good, it's really saying that there's no connection between the variables whatsoever, and the model is useless. So do keep an eye on this p-value, and then also keep a kind of a half an eye on this adjusted R², just to see kind of like how well your model is working. We'll go through these other things in a bit. I think we'll go through those, I think, in the next slides. I don't want to get too far ahead. Actually, you have slides that discuss these other values. The next thing I talked about, I think, is, I'm just going through this function again, is I have this tell me why. And what this is really doing is if we go back to our model, this model here, we are creating a prediction system here. I'm saying, for instance, if I change the value of x, what happens to my y? That function, this function here, is actually being handled in this function in R. So in other words, I'm able to put my intercept value in there. I have my slope value in there. And that's basically just by going through and going into the model itself and pulling out the first coefficient, which is stored there automatically. And then that's my intercept. My second coefficient is the slope, and that's also in there automatically. In fact, you can find these things yourself by typing model. You have your $sign, and I don't know if you can see what I'm looking at. Maybe you can. But you can see, for instance, coefficients, residuals, effect, rank, fitted values, assigned, QR, DF, residual, X levels, call terms, models. You have all these different variables and different types of information that come out of each model that you could use. Now, we don't talk about all of these things in here because it's just, I mean, I've actually taken a class in regression where all we talked about was seemingly linear models, and we use all of these types of things here. But the thing is, this could easily be a class that would, in fact, it was a class that had two parts. There was a spring semester and then there's a fall semester. And so we spent a year talking about regression models. We don't have that much time in this class here. And so we talk about just the model itself and some of the basics. But if you are interested, though, I do ask you, though, to spend some time. I mean, go to your notes, go online, look around. I mean, actually spend some time reading up on regression models because there's a lot going on there, and they're everywhere. Anyway, so I have this tell me why. This is an equation that a formula that I used. And what I do is it says, I can say, okay, well, what happens if my x is equal to minus 10? I'll just put that in there, and I can say that when my model is equal to minus 10, then I can expect to find something like my y equaling 40.389. Now, one thing I'll show you is I've left open this this plot, and it's kind of hard to see this plot. And unfortunately, I just cannot get this to get any bigger. I can't point to this thing, you can see it. But on my plot that I see here on my right-hand side, where my x is equal to minus 10, find that point between the minus 20 and 0, that line there, and follow the line all the way up to where the blue line, where it touches the blue line, and you'll find that that point is 40.389. Of course, you can't see that value here in the plot, but you can see that it's that's about where the point is. And so this code that I've just shared with you, this allows you to actually kind of like make a prediction here and say, well, what happens if my point is minus 10? Now, another thing that I must tell you is that while it's perfectly mathematically correct to put in the value of whatever this value is here, some enormous 10 million, if I put 10 million in here and do that, that value, though, mathematically is possible to, you can produce a value from your model, but it may mean nothing because the model has constraints. The model is only good for values between x equals minus 80 and I would say x equals 11. Otherwise, anything after that, outside of this range here, you can get a value by plugging into here, but whether that value actually means anything is anyone's guess. And so generally what you want to do is you want to have your model, you want to be able to make predictions only for the realm in which you have data. In other words, my predictions are only good when I'm making them between minus 80 and 10. In other words, where I already have data. Because anything outside of that window means that I'll be getting something which, first of all, can't be verified, but also might just be unrealistic. So there is that. Another thing that we have to deal with, and if you, I mean, this is a function that I put together for this kind of like plug-in things, but in R, it actually has a similar function called predict. And so you can go ahead and just like run predict. You can see down at the bottom here that it's how you can create your predictions for your models. You can actually throw in this predict mod. That's the name of our function that we just created. And this will then allow you to print up a plot or create a plot in which you are just predicting values of your x. In other words, the x values come from my low. They come from here. You can see my low value, my low column. And so what I'm saying is that my x now is just the low values. Here's my y. I want you to create a line equation and then throw in those values from mod and show me where they land. In other words, create a line graph using my model so I can see what the trend looks like. This is exactly the same functionality as this. This just goes, one point by one, point by point. I guess I can always have a recursive system here. Actually, I could throw this thing into a plot equation and get the same idea. But this predict actually just goes into the model, pulls out the coefficients you need, creates the line, and then starts plotting points. And then you can see in this plot what the line would look like. I can go ahead and do another one here where I can just throw in, I can actually get a line where I have the points, but I'm actually adding the smooth geom line here so I can see where what the trend is. Okay, so another thing I wanted to talk about is I think that we're getting kind of caught up here. I don't need to take all your time with all this stuff. Let me just go back to my slides if I can find them here. There we go. I think we've moved on quite some distance here. We have this. Okay, we moved on here. We've built our model. We've talked about our coefficients. We talked about this. We have that forecasting. Yep. One more thing about the forecasting is that remember when I have -10 as my x value, it's going to appear where this red spot is on the left-hand side. You can see that this line that we get on the when we plot this using the predict, you can see that that point is also included in this line. Makes sense. It's just a point on the line. So you might plot your data like this, but remember though that when you plot your data like this, then you don't see, if you're not using like a scatter plot, then you don't see the outliers. You just see the kind of the expected places where these points are supposed to fall, but maybe you don't see, for instance, everything. In fact, you're just taking the points as they are, and you're putting them on the line to see what they look like when they're on the line. But actually, though, your points may not actually in reality fall here. They may be scattered all around this line. And so what I'm saying is your line is going to look like, it'll be this. That's your real data. That's how everything really does fall in reality. But when you build a model and you start working through a model, and you start seeing it like this, then suddenly you start realizing that, wait a minute, this is too perfect. Maybe there's things happening that are not this perfect. Anyhow, that's something to think about. Another thing I wanted to talk about is the intercept terms. So we see that there's this y equals mx plus b. This b, in this case, this slide calls it alpha. And when I learned it, it was actually called b. That was the textbook. But b is your intercept, and that's saying that when x is equal to 0, what is y doing? So here we have two different plots of the same data, where one is the line is going through the intercept, where x is equal to 0, and the other one is going without this intercept here. So we have to ask ourselves, do I need an intercept or do I not need an intercept? When I'm creating my line equation, in other words, when I'm creating this, can I expect that my line is going to go through the x equals 0 and y equals 0? Can I expect that to happen? In other words, am I plotting with this intercept or not? And remember where the intercept is going to come from. We don't forget about this, if I can find it again. Right, well, it's these values here. It's that value there, but you get it out of your model, and it's this right here. So you're wondering whether, should I be using this intercept in my model? Well, this is really where this is on you. This is where you have to make the call. And so the general rule of thumb is this, that if your points are kind of collecting around your x equals 0 line, or if they're collecting around x equals 0, and I think I have a slide around here. Well, I guess, but if they're collecting, or actually when you let me say it this way, when you go ahead and plot everything, if your line makes sense. So for instance, I see that my eye, for instance, sees the trend in the data on the left-hand side here, as the data is suggesting that there's a certain upward inclination. I could potentially argue that the points are kind of creating a line which is floating in space and it's going upwards, positive slope. Now, I would have a very difficult time arguing that on the right-hand side, that my points, and these are both mathematically possible, that my points on the right-hand side create a line that goes straight down, makes a nosedive. So you have to look at your points and see, is it actually helping my model to include the x-intercept, or sorry, the y-intercept, or does it not help my model with that? Here, alpha or A is talking about the intercept. I would say that, for instance, without the A, if I don't include my intercept, it does not help my model. I think that I have to include my model. So what I'd recommend is actually like making two different types of models each time that you do this, where you're using this B value and where you're not using this B value. Plot them both and see which is a meaningful interpretation. This is where the skill comes from being a data scientist. The mathematics is easy because it's always the same type of thing here, but actually interpreting this math, deciding which functions to use and how to think about your data actually is a very important piece here. So you want to actually, your interpretation has to be meaningful. In other words, you look at the data and and decide for yourself, does it seem to help my model when I include my y-intercept, or does it not help my um, you can, I guess, a general sense of looking at something here um, is it does in this case here, do I include my y equals, also my x equals 0? Here's a kind of a difficult, but I think you can kind of get an idea that maybe you can argue that you should not include your intercept. And here's a simple plot of tree growth by rain. The more rain you get, supposedly the more tree growth you get, but up to a point. The more rain you get, then you get flooding and then nothing grows. But here we're saying that no trees grow in absence of rain. But actually, though, the variable here is saying tree growth, and so it's actually supporting the notion that the trees are growing. It's not saying they're dead. If there's no rain, then they're probably dead, and there's no growth happening whatsoever. And so here we're saying that the model where the line, the red model here, the line is actually going through the x equals 0, y equals 0, may not make much sense because you never expect that to happen in reality, where zero rain and growth. In other words, you have rain and then you have growth. And so you'd expect perhaps the green line to make more sense. The actual data would be better explained by not using the intercept. It means that you're creating a model where you do not have. And so when you're actually creating that model in R, what you're doing is you're using, this is a model where I'm actually creating my intercept, where I just have this piece of code here. This is including my intercept. In fact, everything we've been doing up until now has used the intercept. But if I don't want an intercept, then I have this -1 after my dependent variable. And so I just want to show you kind of like what this looks like. You can try this code out at home, but in the interest of time, I'm not going to do that here, but it does work. So here we have our data set that we're working with for crime and the temperature. And we're seeing that, for instance, we have this line that's going through, it's a steady, going through our x equals 0 and our y equals with some y value, but it's a steady upward incline. Now, when we have another model here where we have removed the intercept, in other words, there is no intercept available. We're not here. The blue is we've added the intercept, and here we've removed the intercept when we've created our model, which is done this way. But when we do that, we have this downward kind of. They couldn't be more different, these two plots. And so these are two viable mathematical models that you can create from the same data. The only difference is that you've decided to remove the intercept or you've added the intercept. And so it is up to you, the data scientist, to determine which model actually tells a more truthful story. And that is why I keep going back through this whole class in the very, very beginning, saying that these plots and all this fancy stuff that we do on our screens, they really don't mean much when you can't explain like the reality of the situation. You can't see like what's actually happening in your data, then this model is not going to tell you anything. I mean, you won't know which model to choose. And so what you have to do is you have to go back to the data and try and use that model to explain what's happening in reality. And if you can explain what's happening in reality from that model, then the model is a good one. But otherwise, though, if it tells you nothing about really what's going on, if it doesn't allow you to understand the reality of the situation, if you don't understand the reality, then you'll never know which model to use in that case. But if the model doesn't help you to understand the reality of the situation or doesn't predict realistic types of events, then the model is. And so you really do have to spend some time just studying which model should I use, with the intercept or without the intercept. And that is entirely up to you. And of course, you can always find this by just typing in this summary here. You can find your intercept. Here's some more information about the R squared. I'm going to kind of gloss over this because we've actually been talking about this. The R squared, we have the adjusted and the multiple. Remember that when the R is equal to 1, it says the independent variables are predicting the dependence. When x equal or R is equal to 0, we have no prediction. That means there's really no correlation. Here's just some more code that you can look at that'll show you that these are two things where one thing is my x and my y have perfect correlations. They're mathematically. I think that we're out of time now. I think that when I come back, we're going to talk about the wages that tall people make and the wages that not people who are not Ptolemaic. And we're going to finish up the slides, and then I think that I think we'll move into the next slides. We talk about these, and then, well, anyway, I'll have to decide, but that'll be on Tuesday next when we meet. There's no lab and there's no lab meeting this week, but if you have questions, are there any questions before I go? Okay. All right, so that's it then. I will see you all next time. Get some air. It's a beautiful day. I mean, get outside and breathe this stuff in because it's must let the sun shine on you.